Hello and welcome to our presentation. We are going to be talking about learning to fight Minecraft mobs with deep reinforcement learning. Minecraft is a well-known open-world sandbox game developed by Mojang. The world is made up of different kinds of 1-meter cubes called blocks, and there are a variety of naturally occurring animals referred to as mobs. The largest coordinated effort for making AI agents in Minecraft is MineRL, a Python library that uses a custom modded Minecraft server. MineRL includes multiple gym environments for training and testing Minecraft agents. The MineRL organization also runs the Basalt competition, which is a competition using a set of environments and benchmarks for Minecraft tests. For our project, we specifically wanted to use reinforcement learning to learn how to fight mobs. Ultimately, we created our own fork of MineRL, MineRL Combat. MineRL Combat is a superset of MineRL which contains additional gym environments specifically for mob combat. The three core environments in MineRL Combat are the cow, zombie, and skeleton environments. In this project, we worked almost exclusively with the cow and zombie ones. The MineRL Combat environments are set up in the following way. Each environment contains fixed length episodes of 10 seconds of in-game time. The MineRL server game clock is fixed to 20 Hz, so this corresponds to exactly 200 steps. The reward at each step is a weighted sum of the damage dealt, damage taken, and number of mob kills. We also made an additional environment, Cow Punch Easy, where the cow is not able to move. This gave us a simpler environment to train on, since the agent does not need to run around chasing the cow.
While looking through existing work on the subject, we stumbled upon the Video Pre-Training, or VPT for short, paper published by OpenAI in June 2022. This paper introduces a foundation model for Minecraft agents that are pre-trained on a large dataset of online Minecraft videos. The VPT model is trained on 70,000 hours of footage of people playing survival Minecraft. Before the footage can be used for training, a utility model called IDM is used to label the footage. IDM predicts an action space object, which just means mouse and keyboard inputs, for each frame of the raw data. The VPT model is then trained to predict the action space labels for each frame in the dataset. The author showed results for fine-tuning the VPT model with both imitation learning and reinforcement learning. The source code and untuned weights are available in GitHub, and the model is designed specifically to work with MineRL. In fact, VPT is intended to be used in future MineRL Basalt competitions. The VPT model itself is a machine that takes in raw RGB pixel buffers and outputs action space objects. The action space is a continuous mouse position vector and discrete keyboard button states. The model consists of a base network and two output heads. The base network uses a convolutional neural network, transformers, and LSTM recurrence to generate an embedding for the game state. Coming off of the base network are two heads. The first is the policy head, denoted by pi. This head produces the probability distribution that can be sampled to produce action state objects. The other is the value head, which predicts a long-term reward estimate for the current state. The value head is used in training, but does not directly contribute to the model's policy output.
Here are a few videos showing the default behavior of the untuned VPT model. Usually it would just run around aimlessly punching air. At other times it would break blocks such as wooden blocks and possibly use them to craft sticks or crafting tables. At certain other times it would find mobs such as cows and target them, and very rarely kill them. The first of the reinforcement learning algorithms that we used was the Proximal Policy Optimization algorithm, or PPO. PPO was a good starting point for the project because it is well suited to this specific model and environment for a few reasons. First, it is meant for training deep neural networks. Second, it has a high sample efficiency, which means that it can learn quickly from a small amount of data. And third, in the VPT paper, the authors trained the VPT model with PPG, which is a more advanced algorithm that is a superset of PPO. PPO uses the actor-critic paradigm, where one trains both the policy, i.e. an actor network, and a value, i.e. a critic network. The actor maps game states to action space. The critic learns a value function which estimates the long-term rewards for a particular state. The actor uses the learned value function to guide its policy updates, while the critic uses the actor's policy to update its value function estimate. PPO is an on-policy algorithm, which means that it learns from the data that is generated by the current version of the policy. It works by iteratively updating the policy to maximize the expected reward. One updates the policy network by maximizing a clip surrogate objective function. The surrogate objective involves a clip operation with a hyperparameter epsilon that controls the size of the clipping range. Conceptually, the clip operation is there to circumvent exploding gradients and to ensure that the new policy function is not too different from the old one. The value function is updated using a mean square error loss function that minimizes the difference between the estimated value and the actual value of the state.
With PPO, we train just the heads of the VPT network for faster training, since training on the recurrent base of the model is more computationally intensive than just training on a normal feed-forward neural network. Now, we also use a reinforcement learning technique called phasic policy gradient, or PPG, which is built on top of PPO. PPG requires an extra auxiliary value head that shares parameters with the policy head. PPG uses this additional head to tune the internal representation of the policy network without actually changing its output. The intuition behind this is that what the auxiliary value head learns internally is likely also good for the policy to know internally. Now, in training, there's two phases, hence the name phasic policy gradient. There's the wake phase, which is just normal PPO, where we train the regular policy network and the regular disjoint value network. And then there's the sleep phase, or the auxiliary phase, where we train the regular value network again and the auxiliary value network. We train the internal representation without changing the output of the policy network by adding an additional loss term while training the auxiliary value head to minimize the difference between the original output of the policy and the new output of the policy. Now, there's two ways we can use the PPG algorithm to train the VPT model. One, we can train just the heads, but then we have to add in some of our own shared parameters. Or two, we can train the whole model, including the recurrent base, which will provide the shared parameters that we need. Now, we tried developing algorithms for both of these techniques, we called PPG efficient and PPG parallel, respectively, but we currently only have results to show you for the PPG efficient version, so we'll only discuss that here. So now, it's a very simple change to do this. You start with the regular VPT model, which looks like this. Then you first add on an auxiliary value head by just duplicating the original one. And then you put regular multi-layer perceptrons, or normal feed-forward neural networks, in between the base and the new heads. This will give us some shared parameters in the policy head and auxiliary value head while still having a normal value head off to the side. But since the original heads have already been trained by OpenAI, as well as the VPT base, but these new networks have to be initialized randomly, we don't want to just feed in our good output into just random noise. So we're going to add in some skip connections as well. So they get added back in so the agent can act skillfully from the beginning of training rather than just acting basically randomly if we didn't add in the skip connection.
Throughout this project, we did most of our training on the PunchCow Easy and Zombie environments. We achieved our best results with these environments with PPO and PPG-E respectively. During training, our biggest bottleneck was, interestingly enough, not VRAM but regular RAM. Because PPO and PPG are on-policy training algorithms, we need to collect memories during training in what is called the rollout phase. Each MineRL combat environment runs an entire Minecraft server, which all in all consumes about 4 GB of RAM. We therefore could only train with up to 4 environments at a time, which severely limited how much data we could collect each rollout phase. Our best weights for the PunchCow Easy environment were achieved during our PPO training run. Here, the agent learned to barely move and to spam punch straight forward. Because the agent's eye level is just over the top of the cow, in order to land a punch, the agent needs to punch while squatting or simply back up. It certainly is not the most elegant policy, but it does consistently outperform the VPT model in the PunchCow Easy environment.
Our best results on the fight zombie environment so far have been with the PPG efficient algorithm. The video on the right shows our agent fighting some zombies, and the figure on the left shows the distribution of damage dealt for 100 runs for both the foundation model and our trained model. We can see that there is a substantial shift in the distribution, with the trained model able to get more kills, meaning dealing more than 200 damage, than the baseline model is. This shows that we are able to effectively teach the VPT model to fight zombies with our proposed algorithm. As for the discussion of our results, it was quite challenging to train these models. In particular, we ran into an issue called catastrophic forgetting, where the agent forgets how to do things it's already learned to do, which is particularly problematic with fine-tuning weights that have already been trained. This is evident in the figure on the right, showing the reward plateau once it forgets how to behave well. To address this, we use an extra loss term using KL divergence, a gradient clipping technique, and a small learning rate. This also contributes to the agent losing some of the humanness in its play, which is observable in the previous videos. So we can conclude that reinforcement learning is suitable for fine-tuning this model for predefined tasks, though it does take some tuning to get right. It is not well suited for fine-tuning while also maintaining general good behavior.
Finally, we show a few bloopers which happened during the early stages of development. The interesting part in the bottom left and top right graphs is their sinusoidal shape. We believe that this is due to bugs in our implementation and poor hyperparameter selection. In the bottom right, we have a poorly implemented graphing function, which implies that the actions the agent took advance the game states backwards in time, which is impossible. Finally, here are a few videos of these early models playing the game. One model would simply walk past the target, in this case Cal, another one would just spin in circles, one would walk backwards and stop, and one would just jump diagonally. Anyways, that's all for our project. Thank you guys for watching, and good luck on your final projects.